organization. That is the purpose of this. So we'll continue in the next class tomorrow. Thank you.
ಇಲ್ಲ ತೊಗೊಂಬಂದೇನು ಮೇಡಮ್ ಅದಕ್ಕೆ ಹಾಂ Good morning, all of you. So in the yesterday's class, we have started the discussion about the reliability, and we have also derived the equation to calculate the reliability of any product, to calculate the reliability of any part or product. Now we'll discuss about the reliability of a system. Now in today's class we'll discuss about the reliability of a system. So discuss the reliability of a system. There are two types. The first one is when the system, in a system, the parts are connected in series. The parts are connected in series. And when in a system, the second one, when in a system the parts are connected in parallel. When the parts are connected in parallel. Now first we'll discuss about the system when the parts are connected in series. Let us consider in a system, there are three parts which we say A, B and C, and they are connected in series, and this together is a system. Hmm. It's okay. So these are the parts in the system which are connected in a series. Hence, the system is in series. So let us say this is the input and say this is the output. So in order to get the output from this input, all the parts in a system must be in working condition. That means all the parts must be reliable. If any one of the system fails, suppose I'll consider the system B fails while in operating, then we are not going to get any output from the input signal in this system when the parts are connected in series. So let us consider the reliability of system A as RA, the reliability of system B as RB, and the reliability of system C as RC. So if in working, if the part B fails, then the reliability of system B becomes 0. Hence, we are not going to get any output. So the reliability of the system when connected in series is given as the product of reliability of A, reliability of B, and reliability of C. So consider if the part B fails when working, then the reliability becomes 0. If this becomes 0, for this system connected in series, the reliability of the system is the product of reliability of A, reliability of B, and reliability of C. In that case, if the reliability of B becomes 0, then the reliability of entire system becomes 0. Then the reliability of entire system becomes 0. So this is very important. For a system connected in series, the reliability of the entire system is nothing but the product of the subsystems connected in series. Now let us consider the system connected in parallel, that is B, wherein parts in the system are connected in parallel. Parts in systems are connected in parallel. Let us assume this is the input, and we'll just assume two parts, part A and part B, and this is the output. Here in this case, part A, part B comprising the system are connected in parallel. So by any given chance, if any of the part fails during working condition, whether we are going to get the output or no, it is yes. So now consider in working, the part A fails. We are going to get output or no in this condition? The answer is yes, because the input flows from here and it goes to part B, and from part B we are going to get the output. So, but instead of part A, if the part B fails, then again we are going to get the output in this condition also, because the input flows from here to the part A and then to the output. Suppose if both the parts fail, then only we are not getting any output. Hence, we can say that the reliability of system when parts connected are in parallel is more compared to the reliability of the system when parts connected are in parallel. But for this, we can say the reliability of a system when connected in parallel is given as 1 minus the product of 1 minus RA into 1 minus RB. It can be true for n number of systems. If there are n number of systems, then the formula will become as 1 minus RA into 1 minus RB to 1 minus Rn to 1 minus Rn. Is that clear? So we'll just solve some problems with respect to that. So before proceeding, we need, sometimes it is asked in the exams that prove that for a system connected in series, the failure rates are additive. The failure rates are additive. Let us assume there are three parts, A, B and C, connected in series. And let Ra be the reliability of system A, Rb be the reliability of Ra be the reliability of part A, Rb be the reliability of part B, and Rc be the reliability of part C. And let lambda A be the failure rate per hour of part A, and lambda B be the failure rate of part B, and lambda C be the failure rate per hour of part C. So we know that for a system connected in series, the reliability of a system is given as reliability of A into reliability of B multiplied by reliability of C. And this, we know that the reliability is given as S2 minus lambda ST, where lambda S is nothing but the failure rate of per hour of the entire system. So similarly, we can write it as lambda AT into e raised to minus lambda B T into e raised to minus lambda C T. Lambda ST is given as, just take out minus T as common, it will be lambda A plus lambda B plus lambda C. Hence, we can write minus cancels, hence the failure rate per hour of the entire system is equal to failure rate of A plus failure rate per hour of part B plus failure rate per hour of part C. So for any system, when the parts are connected in series, the failure rate per hour of the entire system is given as the addition of the failure rate of the subsystems or the parts comprising that system. So let's start with the problems. So that is the first one with respect to the systems connected in parallel or series. The following are the reliability requirements that have been set on the subsystem of a communication system. The subsystems are the receiver, control system, power supply, and antenna. Power supply and antenna. These are the subsystems which make a communication system, and reliability of each subsystem for a 4-hour period is given as, for the receiver it is given as 0.970, and for control system it is given as 0.989, and for power supply it is given as 0.995, and for antenna it is given as 0.996. There is a communication system which has the following parts or subsystems, and the reliability of these subsystems for a 4-hour time period is given as 0.970, 0.989, 0.995, and 0.996. So they have asked you to find out the reliability of entire system, assuming the subparts are connected in series. So here they are directly given the reliability of the subsystems comprising communication systems, and they have asked you to find out the reliability of the system assuming the subsystems are connected in series. Hence we know that the reliability of this particular communication system is nothing but the product of the subsystems, that is product of the reliability of receiver into product of reliability of control system into product of reliability of power supply into product of reliability of antenna. So which is equal to so the answer will come as 0.950, which is equal to 95%. So next problem, a unit has a reliability of 0.99. A unit has a reliability of 0.99 for a specified time. If two identical units are used in parallel redundancy, what is the overall reliability of the system? So there is a unit A and the reliability of unit is given as 0.99. If this unit is used as a redundancy, then what is the overall reliability of the system they have asked. There is a part A, and this part A has a reliability of 0.99, and if this part A is used as a redundancy, then what is the reliability of the system? So you can analyze this as there is a part A, and the reliability of part A is 0.99, and it is used as redundancy, that means duplication. Again the reliability is 0.99, and duplication means it is performing the same function of the other. If one fails, this component will work or perform the function of this part. Hence, this system is nothing but the system connected in parallel, and thus reliability of this system is connected in parallel is equal to one minus RA into 1 minus again RA. This will come as point 999 itself, that is 99.9 percentile. The next is, it is desired to have a reliability of at least 0.990 for a specified service period of 8,000 hours. On the assumption of a uniform failure rate, what is the least value of theta that will yield the desirable reliability? So I repeat, it is desired to have a reliability of at least 0.990 for a specified service period of 8,000 hours. On an assumption of a uniform failure rate, what is the least value of theta that will yield this desired reliability? So here what is given in this problem is the reliability of a system, that is 0.990, and a specified time period, that is T, is given, that is 8,000 hours. So they have asked us to find out the mean time between failure. So here we know that the reliability of a part, here it is neither a system connected in a series or parallel, because the reliability is given of only one part. Hence we know that the reliability of this system is given as e raised to minus lambda t. The reliability is 0.990, e raised to minus lambda we don't know, t is given as 8,000 hours, and this is hence just find out the value of lambda. The lambda value or the failure rate R per value will come as 1.25625 into 10 raised to minus 6. But we need to find out theta, that is the mean time between failure, and we know that theta is equal to 1 by failure rate per hour, that is 1 by lambda. So hence it is 1 by 1 minus, so 1 by 1.25625 into 10 raised to minus 6. Hence the value of theta will be it is 796019.90 hours. The next problem, a system has 3 units, so it is given as there is a system which has okay. A system has 3 units with the failure rate of 1.5, 4, 3.8 failures per 10 raised to 6 hours. That means each system has a failure rate. So hence the failure rate for A is lambda A is given as 1.5 into 10 raised to minus 6 failures per hour, and for part B the failure rate is given as 4 into 10 raised to minus 6 failures given as 3. Okay, so there is a system which has A each minus 6 failures per hour. So what they have asked you to find is, for the first bit, mean, and second, the reliability of the system, for time period of 10 hours if the components are connected in series. And third bit, they have asked you to find out same so first we'll find out the mean time between failure of the system. So that is T is to S. To find out T is to S, first we'll find out the failure rate per hour of the entire system. We'll assume that here the parts are connected in series. So for that, for the series, we know that the failure rate per hour of the system is nothing but the addition of the failure rates of per hour of each part. So here it is, there are 3 parts, hence it is the failure rate of the entire system is the failure rate per hour of part A plus failure rate per hour of part B plus failure rate per hour of part C. So here it is to minus 6. So this is the failure rate per hour of the entire system. It will come as 9.3 into 10 raised to minus 6. 10 raised to minus 6 failures per hour. But we want mean time between failure of the entire system, that is theta system, and we know that mean time between failure is nothing but the is equal to 1 by failure rate per hour of the entire system. So here the value of this will come as 6.8 hours. 6.8 hours. Now for part B, for component B, they have asked you to find out the reliability of the system for T is equal to 10 hours and parts connected in series. So I'll assume this the parts are connected in series, hence the reliability of the system is equal to, when connected in series, is the product of reliability of A into reliability of B into reliability of C. So for that we need to find out the reliability of A, which is equal to e raised to minus, for A it is how much? It is given as 1.5 into 10 raised to minus 6. 0.5 into 10 raised to minus 6 and time period is 10 hours. And for B, four into 10 raised to minus 6 into 10 will come here, and for C that is again 3.8 into 10 raised to minus 6 and 6 into time period is 10. will come as 0.999. Again, it will also come as reliability of component B as 0.999 and reliability of C will also come as, hence the reliability of the system is 0.997, which implies 99.7%. So this is B. Now we'll consider C. That we need to find out the reliability of the system when the parts are connected in series. So assuming these three parts are connected in series, part A, part B, in parallel, and part C. Hence, we know that the reliability of the system when connected in parallel is given as 1 minus reliability of component A into reliability of component B into 1 minus reliability of component of C. So the reliability will come again as 0.999, so which is equal to 99.99%. So next problem. Again, a system is connected in series and it has three independent parts A, B and C. There is a system which is connected in series and it has three parts A, B, C, which have a mean time between failure of which there is a system which is connected in series which has three parts A, B and C. And they which have a mean time between failure, that is given as theta A is equal to theta B and theta C, which is nothing but the mean time between failure as 100 hours, 400 hours and 800 hours. There is a system in which parts are connected in series and there are three parts A, B, C, and for part A the mean time between failure is 100 hours, and for part B the mean time between failure is 400 hours, and for part C the mean time between failure is 800 hours. And they have asked us to find out the first bit, the mean time between failure of the entire system of the entire system. This is the first bit. And the second bit, they asked to find out the failure rate of system, the failure rate of the system in failures per million hours, in failures per million hours. The third bit, they have asked you to find out the failure rate of the system. They have asked you to find out again the failure rate of the system in percent failures per 1000 hours, per 1000 hours. And in the fourth bit, reliability of the system for 30 hours, reliability of the system for a time period of 30 hours. And last, they have asked you to find out the increasing mean time failure of A of component A to a 30% of increase in mean time between failure of a system. For the first one, what they was mean time between failure of the entire system, that is theta system they have asked. So to find out the theta system, as we know that it is a system connected in series, and theta system we know that it is 1 by failure rate per hour of the entire system. Hence we need to find out this first. So to find out this, we need to know the failure rate per hour of each components making the system. But to find out that, we need to take use of the mean time between failure of each parts comprising a system. So hence lambda A is equal to 1 by theta A. We need to find out lambda B is equal to 1 by theta B. We need to find out lambda C is equal to 1 by theta C. We need to find out, that is 1 by 100, 1 by 400 and 1 by 800. So unit for all this is nothing but failures per hour. Now then, as we know, it is a system where parts are connected in series. For that system, the failure rate per hour of the entire system is equal to the additive of comprising paths of failure rates. So that is this. So it is so hence will come as so that is A. So next is they have asked you to find out per failure rate of the system in failures per million hours. So initially we found out that failure rate of the system was 0.01375 failures per hour, but we want failure rate of the system in failures per million hours. Million means it is 10⁶. Hence here the failure rate of a system in failures per million hours is equal to 0.5 into 10⁶. Failures per million hour. That is B. and C, failure rate of the system in percent failures per 1000 hours. Failure rate of the system in percent failures per hour. Again, failure rate of the system is 0.01375, but this failure rate of the system in percent per 1000 hours is equal to 1000 hours is equal to 0.01375 in percent, so it is 100 in 1000 hours into 1000, so it will be equal to 1375 failures in percent per 1000 hours, that is 6. This is for the percent and this is for the 1000 hours. Reliability of a system for T is equal to 30 hours. Reliability of a system for T is equal to 30 hours, but we know that the reliability of the entire system is for the lambda as also we know that it is 1375 into 10 for a time period of 30 hours, for a time period of 30 hours. To come as 6.6619, which implies 66.19%. That is D. This is D. And the last bit, that is E. What is the increase in mean time between failure of component A to 30% of increase in mean time between failure of a system. So the mean time between failure of new system is the mean time between failure of previous system, that is 72.73. There was to increase of 30%, isn't it? Hence it is multiplied by 1.30. The answer will come as 94.536 hours. Therefore, failure rate per hour of the new system is 1 by this new theta, which will come as 105 failures per hour. And we know that for a system connected in series, failure rate of the system is equal to A plus B plus C. So this is the failure rate of the new system, that is 0.0105. Failure rate of A we need to find out. Failure rate of B we know is 0.0025, and failure rate of C also we know it is 0.00125. 0.00125. Hence, the value of lambda A is come as 0.00675 failures per hour. Now we need to find out the mean time between failure of A. Failure of A, which is equal to 1 by lambda A. That is theta A is equal to 146.456 hours. So it is approximately 146 hours. Then last they are asked us to find out the percentage increase in time between failure of A. So it is 146. It is equal to 146 minus 100 divided by 100. That is 0.46. If you want to keep it in percentage, it is 46%. If I am going fast in any of the problems, you can pause the video and you can note it down.